Chan.
Okay, so thank you for the introduction, and I'm happy to be here to present the material that we have been working for the AOE project. Okay. So the title is about common platform and standard for compact model development. But before we do that, compact model is a very complicated product to me, and it has different. It has a lot of different stakeholders, for the compact model. So if you look at, when we look at models, what do we want to get, from simulation and doing modeling? For different people, they want different things. Okay. Now, if you start from the bottom, okay, some people want to do simulations or compact model to obtain pre-available data. So there's some new devices which, before you have experimental result, you want to predict the behavior you want to use to do that. But this is actually coming from atomic level simulations, etc. Sometimes people do simulation to understand the physics of the device. Okay. And then, for professors, we use model to communicate and education. So we try to explain to students certain phenomena. Models are very good tools for that. We also go for publications. So if we develop a new model or do simulations, the result can be used for publications. And going up on the chart, it become more practical issue, including feeding existing data, or do qualitative understanding about about circuits. Okay, at the end, we want to do functional verification, etc. So there are different kind of things we want to do in the process. Okay, and then to achieve all these tasks, we require different tools. At the bottom, people normally use numerical model, including atomic level simulation, etc. And on the above, what we care about is speed. So if going down, you want to have physical accuracy. To go up, you want to have speed. So if you want to do numerical simulation, all the way to do functional verification, it takes a long time. Okay? And then sometimes one simulation can take years. Okay, that's not reasonable. So we simplify the process. Okay, we have behavioral models, which will give up a lot of physics. We just want a description of the behavior. Now, compact model is somewhere in between, which try to bridge the behavioral model and the numerical model. Okay, so we are somewhere working here. So as a result of many people working in compact model, have different understanding about what it is. Now, and then I think a lot of you have heard about how to look at model from the physics perspective. I want to give a different perspective to look at under a platform. What it means is, if you want to use a model, it has to be used in some platform. Okay, and the current platform is defined by the spikes. Okay, so let's look at when a model is used in a circuit. Okay, what should the model do? Okay, now. Currently, the model simulation engine is defined by spikes. Okay, so when we develop a model, we say that we have to put the model to be applicable to be used in spikes before it can be useful. Otherwise, it's just a whole bunch of equations. They are not very meaningful at all. Of course, spikes right now, I don't think it is perfect, and it's also very restrictive to me. And spike was developed about 30 years ago, and I don't see much improvement over the 30 years. Okay, so maybe we need a new simulation engine. But before that happens, we still go with spike. Now, if you look at a SPICE engine, when we have a model, what does the model do? Now, a circuit is just different models connected together. So maybe in this example, we have 4 models, 1, 2, 3, 4. They're just models connected together, you form a circuit. In the process, you form nodes. So whenever 2 models connect together, you form nodes. So you node 1, node 2, node 3, etc. And then you form branches. Okay? Now, what does the model do? Supposing, you're given the node voltages. Okay, the 2 value here. This model should be able to calculate the branch current. So this is what a very simple model is supposed to do, like in these circuits. Now, and then in simulations, what is the methodology? Well, if you want to solve this circuit, what we really mean is you want to find out all these node voltages. Okay, so that is consistent. Okay, now, and then how to find all these node voltages? The first approach is the simulator made a guess. So you try to arbitrarily guess, N1, N2, N3, these voltages. Okay? After you made a guess, each model will generate the corresponding currents altogether. Okay. Now, according to KCL, it's the case that all currents going out or coming out or going into a node is zeros at all time. Okay. Now, but at the beginning, you just arbitrarily guess the voltage. So as a result, there's no guarantee that all the current go to any node, it will be zero. Okay. Now, if that's not the case, then the simulator will make another guess. Okay. So that at the end, we hope that after many guesses, it will converge and then obtain the right value for the voltages, which solve the circuit. Okay. And new gases are obtained by the Newton-Raphson methods. Now, let's put it into more mathematical form. Now, supposedly, I define a voltage vector. The voltage vector is just a collection of all the node voltages put together. And then based on these node voltages, okay, and then for the circuit, I can calculate the total current going to node J. Okay, and this is some kind of function of all the node voltages. Okay. And then I can connect all these currents to form a current vector. Okay, so this current vector will tell you all the currents go to all the nodes. Okay, suppose there are m nodes in the circuit with m currents, and then you have m voltages. So it's it's a vector form. Now, given this, what does the circuit simulator is trying to do in the simulation? What it's trying to do is you want to find out all the node voltages, okay, such that all the total node currents or this vector becomes zero. So mathematically, just say that I of v I of v vector equal to 0. Okay, so you want to find out these voltages. Then the circuit is solved consistently. And this becomes a very simple mathematical equations, which we learned in secondary school, except that it's multidimensional. Okay. Now, and then to do that, you can use Newton's methods. Okay. I think most of you know about this, so I don't have to go to detail. But in 1D, basically you want to guess a solution, and then you linearize it based on the slope you found the next solution, etc. Now, in vector form, we make the next guess based on the current guess, the current value of the currents, and the derivative, okay, of the current value with respect to all voltages. And the derivative of current with respect to voltage is just the conductance. So this becomes the conductance vector. After that, you can multiply the G to both sides, or just multiply by the inverse, okay, of the matrix. Okay. Then we have this O-form matrix, okay, which the next guess is coming out from current guess, the derivative current guess, and the current value of the function. And if you expand this, okay, it looks something like this. Okay, these are the derivative of all the currents. Okay, these are the voltage you want to solve. These are all the currents. These are all the derivatives there. Okay, and then based on this, you can get the first guess, and then keep on iterating until you find that the current I becomes 0. And then you say you solve the circuit. So this is what SPIKE is doing. So SPIKE to me is nothing more than a linear equation solver. So it's a very simple program. Actually, SPIKE was initially developed by an undergraduate project, okay, at Berkeley. So it's not that complicated at the very beginning. Of course, right now, there are many sophisticated algorithms in SPIKE, including the star matrix, the convergence algorithm, etc. Many things has been added to make it a very useful software. Now, given this, okay, we can start to understand what is required for a model. Okay, so model is not just equations. Okay. So when you have a model, okay, you have you want to put it in the simulator. What the model really does is it fills in the Jacobian matrix. Okay, and then let the simulator iterate, okay, to solve the solution. Okay. So and then in certain simulation, there are also different kinds of simulation required. For example, in DC, transient, okay, and frequency domain simulation. These are the most common ones. Okay. In DC transfer function simulations, okay, the model will try to produce accurate IV equations. Okay, so you want to make sure the IV is accurate. Okay. And then you want well-behaved and reasonably accurate conductance, and this mainly for convergence. Okay. What it means is you can have a model which the IV is accurate, the conductance can be wrong. But for DC simulation, you don't really care too much about that. Okay, about convergence. Of course, the result can be wrong, but you converge in some sense. So this one example like this. For example, in some model, the velocity and E field, suppose that there's a smooth transition like this. Okay. But some model get a discontinuity, okay, at some point because they use the piecewise model to connect it. So if you iterate in this region or this region, you're fine. But if you iterate in this region, if you go back and forth, you may have convergence issue. But this may not affect the accuracy. Okay, so some model pass, okay, this test, okay, but if you go to simulator, okay, it may cause problem if you're simulating around this point. Well, you can also require some time domain simulation. This is more involved. Okay. Besides IV, you also require QV because you have a DQ, DT, the transient current. Okay. And then sometimes, okay, if you have inductance there, okay, you have flux V equation as well. But fortunately, I think up to now, people are only considering linear inductance. We don't have any nonlinear inductance, so we don't have to worry about too much about this. Okay. And then we need well-behaved conductance, okay, and capacitance, or sometimes inductance for convergence. Okay. So in transient simulations, okay, if you don't care too much about the harmonic, etc., okay, then this is good enough. Okay, because in transient simulations, circuit designer normally only look at the delay. You don't really care too much, okay, about the harmonic distortion, etc. Okay, especially for digital circuit. Okay. Now, for frequency domain simulation, it is different. Okay, because it's more like for the for the analog circuit people. Okay, so the IV equation is important, but mainly to give the biasing point. Okay, after you get the biasing point, you don't care about whether it's correct or not. Okay, and then you want accurate first order derivatives to give you the conductance, to give you gain. Of course, if you want to go to other simulation like harmonic balance, etc., you want to have an accurate second order, even third order derivatives. Okay, but this in the frequency domain simulation, because everything is linearized, okay, derivatives become more important than IV. Okay. But on the other hand, in many cases, okay, say in digital circuit, we may be concerned about the time domain or DC structure simulation because we only care about IV. We don't care too much about the CV, okay, or the conductance. Okay. And this is especially true when Berkeley Royal BC1. It is something that we call that the DC model, okay, which okay, the IV is correct, but all the conductance are not that perfect at that time. Okay. Now, given this, okay, what are the model options? Now, model is nothing more than just a black box. Okay, if I give you the voltage, the model needs to produce the currents and the derivatives. Okay, so there are many options in the process. Now, the first, okay, or the simplest one, or feasibly correct one, is numerical simulation. Okay, basically you get a set of differential equations, either you get either the Poisson equation, Joule diffusion, or even go to more first principle, the non-equilibrium function, Schrodinger equation, etc. These are solutions. These are models that cannot be solved analytically, and then you want to have numerical solution. So you have a numerical simulator at the end. Okay. And the input is a structure, okay, boundary condition, etc. Okay. And then you get the IV. Okay. And this approach is the most accurate because you can if you know the structure of the device, you can really draw the structure out. Okay. And then what you simulate, okay, will represent the new device in that case. Now, on the other end, okay, what you need, okay, is only if I give you a voltage, you have to generate IV. So you don't need any equations. You don't need to know anything about compact modeling. What you do is I can go to foundry, okay, I need to use only maybe 10 transistors in the design. I make that 10 transistors, okay, in my layout. Go to foundry, get a chip back. Do all the measurement. Make up a table. Okay? After I make a table for all the voltages, okay, I get all the currents. And then after that, okay, when you do simulations, when your voltage is being produced, you just come to the table and make a guess. And again, find the value there. This is already a model. Okay? So basically the input more particularly is to get data point. Okay? You put this data point in the table. Then someone may ask what happened in between. Now it's very simple, just do linear interpolation or something else. But that also creates some problem. The problem is, well, you can say that the line linear interpolation will be okay, but between two pieces, the derivative may not be continuous. You get breakpoints in the process. So you may need about cubic interpolation, etc. Okay, to make the derivatives move as well. Okay, so you need some kind of interpolation techniques to connect different points together. Okay, so this is another approach to do model. Of course, in this case, if you use only 10 transistors to extract the data, this set of data cannot be used to predict the 11 transistors. So there's a limited predictability in the process. Okay, but this approach is very accurate. Okay, and actually has been used by many designers when the model is not accurate enough. Now, compact model will present something in between. Okay. So it can be something like a table lookup, which I don't care about, when you get, just give me the data, I fit it, okay, or getting closer to physics. So the input is analytical equations. Supposedly, it's explicit, which I give you explicitly what are the currents, okay, what are the derivatives, and then you get a continuous line of IV versus of I versus V, okay, in the process. Now, and then in between, okay, you have a lot of trade-off to do. You can make it very physical, which is called the numerical simulator. Okay, at the same time, it's physically correct, but at the same time, the speed is very slow. If you go down this way, you can make a compact model which is close to table lookup, which physically is totally wrong, but it can run very fast. Okay, so there are different trade-offs in the process. Okay, so a compact model can run many different kind of model along this line. Okay, so that's why there are so many different kind of model exist. in the process. Now, so if you look at compact model, okay, it represents a trade-off between physical accuracy and efficiency, okay, in the process. Okay. And of course, different people have different needs, okay, in using the model. Okay. Now, and then when you develop compact model, there are also two different approaches, okay, in general. One approach is called empirical approach. Okay. So what it does is, I don't care about what the characteristic is, I don't need to know the physics. Okay. I look at the data, I treat the whole thing like simple curve fitting exercise to match all the available experimental data. You can say that the early classical model of MOSFET is some kind of empirical model because you look at the shape, it looks okay, devise some physics with some iteration, come up with some equations. Okay. The equations seem to be like they have the same shape, okay, and then as a result, you say that it's more like an empirical model. Okay. Now, for this kind of model, if you want to simulate the device, okay, which is already in the, within the data set, then this simulation is very correct, it's very accurate because based on the data, we produce the same data. Okay. Now, but in the process, discontinuity may occur, especially in the derivative, okay, if you do this. Okay. And I would say, take a look out. Probably it's an extreme case of empirical model. Okay, because basically each data point is one parameter. So you have an extreme case of empirical model is actually take a look out. You can use a physical approach. Okay. Now, in a physical approach, the model was developed based on the physical parameters such as insulator thickness, doping concentration, etc. Based on those parameters, you write the equation of the device. Now, in this kind of model, it usually can be used to predict the transistor behavior outside the test set. What it means is, I can measure 10 transistors, but using the same parameter, I can predict the behavior of the 11th transistor. So this is the advantage of physical model. But this has some problem. To develop a correct physical model, you have to understand the physics first. Okay. So as a result, this model normally will be developed later than technology development because at the very beginning, people put in some new material, put in some new structure. We don't understand what is going on. At that time, it is very difficult to develop a physical model because we don't understand what is going on at that time. Okay, so now it's developed later in the process. Now, and then there's so many confusion about models. Okay, and then some companies come up with an idea. Okay, they want to have an industrial standard model. Okay, so the industrial player do not want to support many different models in the process. So the founders say that if a customer went to them, they want to have a model, they want to support only one model. They don't want to provide PSP, PSP, so many different kind of models. So they want to have a standard, okay, so that the entire industry try to use the same model, so it's easier for communications. Now, because of that, the Compact Model Council, the CMC, was formed, okay, to oversee the compact model activities. So CMC, right now, I think it's changed the name to Compact Model Quality, okay, so it's changed the name there. Okay. Now, but in the process, the company just want to get together to somehow define a standard. Okay. And BSIM3v3 from UC Berkeley was the first standard model selected by CMC in 1996, followed by BSIM4 in 2000, and then PSP in 2006, okay, and then potentially it's BSIM6, which in the near future. I think it has not been standard yet, okay, from what I understand. Okay. Now, but the process to me has some problem. Okay. If you think about a standard, okay, a standard normally try to help people to work together, come up with joint force to work on the same thing. But I think the industrial people, when they define the standard, they only have a problem they want to solve. Okay, they do not really care how to solve the problem. Okay, and then they also worry a lot about the programming side, okay, of the problem. What it means, I remember at the time we discussed one issue. Supposedly you have one model. Okay, you can have the same equations. Okay, but when you write the equation, mathematically they have different form. For example, a times b plus c and a times b plus a times c, mathematically they're equivalent. But in computer, when you write that into different form, due to numerical error, they can produce different results. And this error can accumulate. So they're very afraid that the different code can produce different results. So to avoid this problem, okay, they try to standardize not the interface, okay, not the equations, but they try to standardize the source code. Okay, to me, it's very questionable, but this is how it's being done. Okay. So they hope that the source code, when it's standardized, you move to different platforms. In some platform, that platform, PC platform, they all produce the same result. Okay. But to me, it's not realistic because the compiler is different. The compiler different CPU, it should still all be different. But again, the people also think that, well, one step closer to the source is better than like very far further away. So what it is only compile this, so you can solve the problem there. So this is like how we do it. Now, because of this, you create a lot of problems. When I was at Berkeley, I found that I spent most of the time to defend the model. Because once you become the model, everybody else are not the model, right? And then what they do is they try to find all the problems you have. So that they found that their model being developed by their group is better than the standard. So they can publish paper. So at that time, Berkeley keep on receiving attack, like different things that put together. So I spent a lot of time defending the model. Okay, so this creates a very keen competition. Okay, now and also when you standardize source code, there is a problem. How do you ensure the source code are the same? Now this is how it's being done. The coding can only be done at Berkeley. What it means, I did the coding myself, so I know I have to code there. Okay. And then if some company found that there are some problem in the code, say Cadence found that I did a very poor job in the coding, okay, they are not allowed to change the code themselves in their product. Otherwise, they do not conform to standard. What they should do is they should tell Berkeley what is the problem, or give the code to Berkeley. Berkeley will be responsible to integrate all the codes together, and then in like some kind of interval, maybe every 3 months, they have a new release. And then the company can take the new release, okay, with the bug fix, and put it into the standards. This is how it's being done. Okay. So the code can only be done at Berkeley, okay, with regular updates. This is how it's being standardized. Okay. Now, to me, there are a lot of problems in the process. Okay. First, okay, I found that it's in the group, Berkeley is spending a lot of effort to support the model. Okay, it's a very time-consuming and also a very very tedious job to support all the requests from different industries. At the same time, the code are not optimized. Why? Well, in a university, people come and go. Right? So I come in, I have my own programming style. So I have my way of naming variables. So I will stay for some time, and then before it's standardized, I left. Somebody else take up my code. They do their own coding. They have different coding style, different way to name variables. So altogether, you found that the code right now become very messy because I go back to look at the code again. I found that I don't know what the code is. Of course, at that time the code is C code, okay, so C code is more messy. But I hope if Verilog A or in MATLAB code will be easy to read. Okay, this is the situation. Okay. So as a result, the source code right now is not optimized. Okay, in industrial models. Now, but on the other hand, okay, this will not be avoidable because if you want to understand how models are being used in industrial environment, okay, it is totally different from the academic environment. Okay. Now, first of all, in a company like Intel, okay, they have technology being developed, okay, and at the same time, they have to design the circuit already. So when the technology is ready, they can have a product available right away. They cannot wait for the technology to be stabilized, okay, before they make the circuit design. Otherwise, they will delay the product. Okay. So as a result, okay, circuit design needs to go together with the technology. Okay. But at that time, the device structure has not been finalized. The device characteristic is unknown. Okay, so this is a situation. Okay, so what it means is, and also at that time, I should not say that the device is not unknown, but not fully understood because there are many new data coming out, new material coming out in the process. Okay, and many variations of process with different device structure as well. Okay, what it means is, when we develop a model for a standard, say 65 nanometer technology, IBM is doing something, Intel is doing something, they may not be compatible with each other. Okay, structurally they are different, okay, in the process. Okay. Because of that, okay, you need many parameters to adjust the characteristic of the transistors. Not because, okay, it is not, not because, the model is physically incorrect, but simply because, okay, I don't care whether it's physically correct or not. You have two transistors, they are both MOSFET. Even they're not totally different, okay, structurally. But the model has to be able to predict both. This is a requirement, okay, for industrial model. Okay. So remember in BCM3, when we first roll out BCM3, we only have about 30 to 40 parameters. When we first come out being standardized, okay, it becomes 120 something parameters. Including BNA, go to about 200 parameters. So the parameters keep on increasing. Okay, because we have to fit data, whether they are good or bad, okay, they're the right, they even may not be MOSFET, we still have to fit them. Okay, so this is the problem. Okay, so as a result, industrial models tend to be more empirical in the process. Now, unless you have a structural description language to describe the structure into spike-like simulator, otherwise this cannot be avoidable. Okay. Now, and then after that, BC was selected to be the first industrial model, okay, because it's really trade-off physics for practicality. Okay. Now, I remember BC was first developed by my former supervisor, Professor Pinko. Okay. Later on, it was transferred to Professor Chan. But Pinko is the first one who developed BC. Okay. And then when BC was selected to be the model, I actually asked Pinko, what is so special about BC that is being selected as standard? And he told me the answer is, BC is willing to give up physics. It's what makes it special. Okay, because many models, they're so concerned about physics, make everything lump together. Not very easy, to modularize the structure, and then not easy to add new parameter into the model. As a result, it's less practical for industrial usage. Okay. Now, in that case, the model is not very accurate. So basically, the model getting closer to something called universal curve fitting. And then the accuracy of the model is being pushed to the parameter extraction process. Okay, so the model does not need to be accurate. As long as you have enough parameter, you can fit almost anything. Okay. Now I remember this one story, a gentleman who actually present, keynote talk in the VLSR symposium. Okay, and then he tried to promote BC4 model. He tried to say that BC4 is so good that he can even fit the double gate MOSFET data. Is what he tried to promote this. When I listen to this, he think that is an advantage, but to me, I'm a little bit fussy about this. The reason is, if you look at the physics, okay, of bulk MOSFET, okay, and double gate MOSFET, even they're similar, they're actually quite different, okay, in some detail aspect. Okay. Now, you use a wrong physics, you can fit a double gate MOSFET characteristic. That doesn't mean your model is feasible. That means the reason why BC4 can fit the bulk MOSFET data, it's not because of the physics is correct. It's because you have enough parameters to fit all those data. So BC somehow become to me is something like a universal curve fitting. Okay, which can fit almost anything in the process. Now, and then if you look at the trend of parameters, okay, this to me I call this the Moore's law of parameters. Okay. So for every fixed period of time, the number of parameters doubles. Okay. So at the very beginning, the level 1 model is very simple, only less than 10 parameters. You go to BC4, we're getting closer to about 400 parameters. Now, PST when we first developed, it get only 30-something parameters. But when it becomes the standard, including Phoenix, it gets close to 100-something parameters as well, if you want to use the full model. Okay. So then this number keep on increasing. Okay. Now, when I showed this picture to Chan, I think he did not like it. Okay. He said that BC is being criticized for having too many parameters to begin with. And I showed this saying that with many parameters, it's showing our weakness. Okay. So I fine. I told him in that case, we try to make the picture in a different way. So I try to draw the line. Okay. It's called parameter per features. So what it means is if you want to have more features, okay, then you add some parameters there. The reason why BC has so many parameters is because it has many features. Okay, so I think he's happy with this plot. Okay, overall. So in some sense, okay, it's also true that if you look at the advancement of transistors, okay, from the early day to the current structure, there are many new physics, new material being added to the transistors. As a result, we need more parameter to fit the data. Now, in addition to a model, okay, each model should come with a specific parameter extractor to be useful. Okay. Now, so what is a parameter extractor? Now, it is a software, okay, which you are given a set of parameters, say I say P1 up to Pn, say you have n parameters. Okay. You want to pick this parameter such that the error between the model predictions and the experimental data is minimum. So mathematically, it is what should be written there. For example, these are the experimental data. So you get the DI, this individual data, measured at certain kind of VG, VD, VSDB. So these are measurement data at certain bias condition. Now, using the same bias condition put into the model with one set of parameters, it produces a prediction. Supposedly, the model is very accurate with this parameter, then this error should be very small or close to zero. Okay. You look at the difference between these predictions, okay, and the measurement data, square them, add them all up. Okay. This is like the total, some kind of the square of the total errors. You want to find out the parameter set P1, P2, P3, Pn, such that this error is a minimum. So this is the goal of a parameter extractor. Okay. So of course, you can do it in a different way. You can treat this as a physical approach. You can use it, or you treat this as a mathematical approach. There are different ways to do this. Now, and in some sense, okay, if we look at we develop models, we cannot earn anything by developing models. okay, because nobody will pay for models. Okay. But parameter extraction is what the company is willing to pay for. Okay, and we also get a lot of consulting job just to extract parameters. Okay, so in some sense, okay, this to me is more important, okay, than the model development. Okay. So a good extractor can make a lousy model, okay, if you have enough parameters, okay, accurate. So this is what the industry is doing. So as long as the model has enough parameters, okay, then you have a very good extractor. You can almost fit anything. Okay, so this is what the current practice is. Now this is a table I got from Microwave Magazine. Okay. What they try to do is they look at the interchangeability of models. So they look at they try to use different models to model gallium arsenide and silicon different MOSFET. Okay? They start from different things. So initially, these are the model name. Okay? They are originally used for gallium arsenide, LDMOS, SOI, HAMS, etc. They try to use all this model to model these devices. Okay? They look at the performance. They can all fit very well. Okay, so what it is, you don't need a gallium nitride HAMS model, okay, to model it. Okay, right now there are also the process. Okay, so this is a result people have been discussing about compact modeling. Now, so I talked quite a lot about industrial models. Okay. This is what the industry is practicing. Okay. But what about academic models? Okay. Now, if you look at compact model, to me, it should be subcategorized into academic model and industrial model. Okay. Because academic models are useful tools to understand the physical behaviors of transistors based on simplified structure. So for physical model or for academic model, we always start from idealized structure, uniform doping, etc. to begin with. Okay. Now, in general, academic model is more appealing to the common sense of researchers. So we like it. Okay. As myself, I like academic model better than industrial model. Okay. And in some sense, okay, it's also good for publication paper. Okay. But if it's purely physical, okay, then in many cases you cannot use the physical data well. Okay. Unless those are very well controlled physical data. Okay. The reason is because the model can be correct, but the device is wrong. Okay, you're not making an ideal device. There's so many non-ideality in the process. Okay, and in some sense, I always try to ask the question: you get the right model to predict the wrong device, and you have a wrong model to predict the right device. What's different? Of course, in real case, probably with a wrong model to predict the wrong device to begin with. Okay, so this is the situation about modeling. Now, and then compare industrial model and academic model. There are also different approaches to handle extreme operation regions. Now, let's see what happens. Okay. One case, what I will try to look at is the breakdown of very power devices. Okay. And in industrial model and academic model, they're being handled differently. Okay. Now, you have breakdown characteristics. Okay. In industrial practice, okay, you try to operate the device not in the breakdown region. Okay. Basically, the breakdown region is basically out of the question. Okay. If you go there, okay, somehow you should throw away the device. Okay. There's no reason to predict the behavior after breakdown. It's useless. Okay. Now, if you develop a model academically, you should be able to predict the breakdown behavior at the very far end. Okay. Because in the simulation, you don't know what people put in the number. They can put in some value, which is like 1 million volt. Okay. Then the model should behave correctly. Right? Now, you have two choices. Suppose you get a very good equation, okay, about a breakdown. For a academic model, you should predict the breakdown behavior at 1 million volt. But in an industrial model, this may not be the case. The reason is you won't be operating in that region. What you care about is convergence, right? So and then in a circuit simulation, well, you may not go to 1 million volt by user input. But in the iteration process, you don't know what the simulator will guess. The simulator may guess a very unreasonable answer, right? You guess 1 million volt, it's coming from there. So if the simulator guess a incorrect range, if you use a correct equation, you try to iterate in the wrong region, right? Because we are using different equations. Compare that in the correct region. So you should try to extend the equation in the correct region to those parts so that it helps you to converge back to the correct operation region during iteration. That's my point, right? So sometimes, okay, some people argue that at that voltage, maybe in some models, we are doing memory model. So in PCM, patient memory model, in some current, the material should melt. You should predict the melting resistance, okay, of the PCM. But this may not be very useful because, we do not operate that region. Okay, but somehow if you incorporate those equations, you actually have the convergence, okay, of the model. So this is a different way to handle academic model or industrial model. So if you want to publish paper, you give a wrong equation in the melting region, right? People say that you're wrong. In the industrial model, we don't care too much about that. What we care more is about convergence. Okay. Now, many device models published in the literatures are incomplete, cannot be directly implemented in the simulator, because sometimes the derivative are missing, there are implicit parameters, etc. There are many issues. Okay. Now, and then PSP starts out as an academic model. I like that at the very beginning. I found that a very elegant way to solve the circuit potential. But when it became the industrial standard in 2006, and then people found that somehow it's getting closer and closer to DC. Because the people added parameters there in the process. Okay. And then finally people found that they will go back to DC due to many reasons, including speed and other issues. Now, these are the classical approaches. Okay. Now, there's no standard in a well-defined geometrical. If you look at the model beyond classical transistor models, there's no standard and well-defined geometrical structure in the process. Experimental data are not readily available to fit experimental data. So if you want to develop a model, these are different issues. Okay. A lot of data published, but most of the models are incomplete and cannot be implemented in the circuit simulator. Okay. And not easy to compare models as they require a lot of work to understand and implement the model in a different way. Okay. Now, despite the less structured process to connect technology and design, compact model still remains as the most important link of the two worlds. Okay. Because of this, we look at the lifespan of compact model. Okay. If you look at a compact model, sometimes people develop partial model, and then you publish paper, and then it's the end of the story. Nothing comes out. Some people further refine the model, and then publish another paper, then another end of the story. Okay, just and then people forget about this. Actually, people also ask, after I publish a paper on the model, what can I do with the model? They have no idea what to do with that. And then, if this has to go downward, you have to go for completeness. Make sure all I, B, C, V derivative are complete. You may need to do some more mathematical modifications to make sure the equation is efficient and smooth, etc. Then you have to implement the simulator. Okay, and then you go to documentations. Okay, this becomes academic model, which will be used for propagation, etc. And then for some model, you do some convergence. You have to solve the convergence issue, make it go faster. You have to do verification testing, and then you have to develop a very good parameter instruction methodology. Then this will be available in tools. Okay, this model can excel. And then if you look at that, over 90% of the model get killed here. Okay, and then only very few models can come to this level. Okay. So, in recognizing the importance of compact model in this regard, we try to reduce the cost to go from here to here. So as a result, we develop the IMOS project. Okay. We try to bridge the two gaps. Okay. Now, the IMOS project supposedly is another presentation, so I don't want to go too much about this. Okay. And this is only a user interface, basically to have the model here. Okay. You can implement models into this website, and then people can look at the model by entering some parameter biasing, and then the characteristic will be shown automatically. So this work has been developed to bridge the two worlds. Okay, and then you can also compare data with experimental results. Okay. We can also do circuit simulations. Well, sometimes we skip a little bit. You can also do circuit simulation in the process. So the IMOS is intended to give the model developer and the people to get early access to the process without going through try to simplify the intermediate process to go from there. I think it's actually similar to this project, which Mark mentioned in the first day of the presentations. But this one starts from, I think it's from the upper triangle. We go from the top down to see what the user really needs from the model for the model, and we try to bring the model to the user. Okay, this is what we are doing in the process. Due to time limitation, if you're interested in what about the IMOS list, you're welcome to go to the website, and visit us. This is for free. You can just register for it. You get a user menu there. Then you can understand what we are doing. So that's all. Thank you.
The presentation is open to questions. Any questions?
So, what are they asked? So the goal here is to understand performance, right, for a variety of platforms. But there are certain applications where you do want to see what happens at extended conditions, right, the non-operating conditions, when you want to look at things that are related to reliability or potentially yield. You get a sense that parameter extraction that gets done here can be applicable to some sort of scenario like that.
Okay, it is correct. Okay. That's a two-part of the presentation, okay, which are to extend together. Okay. So the first part, I explain what the industry is doing things nowadays. So I'm not saying that we're doing something right or wrong. So this is only I explain what is going on nowadays. I totally agree that for reliability simulation, we have to look at extended operation condition. Okay. And reliability also, is another issue, okay, because spike will not provide a very good platform for reliability simulation as well. So right now, all the things I described there, okay, is under the spike platform. This is our constraint, okay, because the industry only understands spike. Okay, so this is the standard. Okay. Somehow, if you can improve the spike platform, it can be done better. And Berkeley also developed another reliability platform called Berkeley Reliability Tools. There's another platform for that. Okay. So in a reliability simulation, that may not be transfer function, transient, okay, and AC simulation. Okay. That will be a totally different scenario. Okay. So that what kind of model is suitable for that application? I'm open to this. Okay. So right now there's no conclusion on that.
Yeah, no, I think that's an important point because when you get to the sorts of conditions of physics, really have to be pretty well understood.
Yes, okay, but if you take a look at publications, right, there are two different papers. Oh, reliability is one paper, okay, and model development is another paper. So the readers, okay, have different perspectives to look at them. So I think one problem for compact model is so confusing is different people only look at part of it. Okay, and assume that this is the whole of compact model. That's why there's so many different arguments that nobody really this is just an integrated behemoth of so many things together.
I have a question. Since you're not interested in the physics.
I'm not saying I'm not interested in physics.
No, I mean, in the end, you say eventually it's not physics as important as
well, this is what industrial practice is, not me.
Okay, that's fine. Sorry. I wonder if the neural network people ever invaded your community. They have a lot of this parameter fitting and optimization.
Yes, okay. I think people are talking about neural network, kind of simulator. Okay, but in that approach right now, it's still very, very slow. Okay, so it's the speed issue. The reason why we don't care about physics, we want to go for table lookup is because of the speed. Because lookup table is very, very fast.
Just a very simple question. What is new in BSIM 6 compared with BSIM 4?
Well, actually, this is an interesting question. Okay. Now, when Pinko developed BSIM, he has different idea of different generation in the process. Okay, so BSIM 1 is we just want to please the sponsor, SRC. Okay, so the rollout is the so-called the DC model. Okay, BSIM 2 is some kind of AC fitting order derivative and become a semi-empirical model. BSIM 3 is supposed to be physical. To keep BSIM 4 should put down should have all the parameters with the minimum correlation to have for statistical modeling is what he put in BSIM 4. After BSIM 3, okay, he left, and Chan will take over. Okay, like there. And Pinko and BSIM and Chan have different kind of personality. Okay, Pinko is I mean, from what I understand, he's the kind of person that everybody are wrong except him. Okay, so they don't understand what is going on, so I'm doing the right thing. And Chan is more he's trying to please different people, trying to find a compromise. Okay, so BSIM is actually both professors have very strong contribution to that. Before Pinko, before BSIM, without Chan BSIM won't move to this stage. So after Chan will take over, then BSIM become to me is a group project of different people. It's no longer the pure project of Berkeley. Okay, so people don't really go back to revise the philosophy of model. Okay, so they look at more new features, new physics put in there. So BSIM become an integration of more features. So BSIM set to me is first of all, you try to correct some problem that BSIM 3 has. Okay, including the symmetry issue, all these kind of things. Okay, and then getting to and then adding more new features suitable for 45nm technology. So it's guess to be an incremental development from BSIM 4. There's no philosophical change in the process.
Okay, because of time constraint, maybe we should move on. And thank you very much. The next speaker is Professor Jen Wong.